So now we turn to scattering experiments. Remember, in the two-body problem, you had, depending on the type of potential and depending on the energy of the system, you had different types of motion. There was bounded periodic motion. That's what we focused on when we considered the Kepler problem and the orbits of planets around the Sun. This was bounded periodic motion. But then there was also scattering. Scattering was characterized by the fact that in the we are considering now the effective one-body problem. So you have the center of the potential, and in the scattering case, you have a particle approaching from infinity, reaching a certain minimal distance to the center of the potential and then going off to infinity. And these gray lines, they characterize sort of the asymptotic trajectory of the particle. One says that these particles, or this particle, is asymptotically free, so far away from the center of the potential. It moves like a free particle, it performs uniform motion, then it approaches the potential and up to some minimal distance rho min, and then it goes back off to infinity, and where far away from the potential it then moves like a free particle again. In this one-dimensional picture, remember, that corresponded to the following scenario. We have here the effective potential as a function of rho. We have here some curve, and we have the particle coming in at some energy E, coming in from infinity and turning around, and the turning point is at this minimal distance rho min. Well, there are many reasons why the scattering case is also very interesting. One of these reasons is that one often performs scattering experiments, and they offer a way to learn about an unknown potential, especially if you are at atomic or nuclear scale or even smaller scale. You want to understand the interaction between particles, and what you do is that you shoot particles on a target, on other particles, and they are scattered off. You measure the distribution of angles, of scattering angles, and then you try to infer from that distribution something about the potential, and that is the forces between these two particles. Let's have a look at the experimental setup for such a scattering experiment. We are now talking about we're still in the picture of this effective one-body problem. So we are not talking about two bodies here, but we are talking about one effective body scattering off a fixed external potential. This gray line represents the beam axis. Somewhere along this beam axis is the center of the potential, and we call that the target. And at that point, there's also the origin of our coordinate system. So here is r equal to 0. We are going to use spherical coordinates, and there is the origin, r equal to 0. So we have a fixed target, and this is the center of our potential. And that's also the origin of our coordinate system. Now, in come particles that scatter off this target, this potential. These incoming particles we call projectiles. And they are not all exactly on the beam axis, but the beam has a finite size, has a finite thickness. Yeah? So you will have projectiles coming in at varying distances from the beam axis. They're all moving parallel to the beam axis, but they are not exactly on the beam axis. Yeah? So these are our projectiles, and they have masses mu. That comes from the reduced mass that we have in our effective one-body problem. One important assumption is that these projectiles inside the beam, the beam consists of many, many projectiles, and we make the assumption that these individual projectiles are independent of each other, so they don't interact amongst each other. Now let's pick out some specific projectile. Now this projectile will be scattered off the target, the center of the potential. It has a certain distance from the beam axis. This distance is denoted by S, or we shall denote it by S, and is called the impact parameter. Now, as I said, asymptotically, far away from the target, the projectiles are free. So far away from the target, the projectiles move parallel to the beam axis, and then the incoming projectiles, the outgoing projectiles far away from the target, they will also move like free particles on some straight line. So asymptotically, the particle will approach this straight line. This asymptotic trajectory, linear trajectory, is tilted against the beam axis by some angle theta. And that is the scattering angle, or it's deflected by some angle theta. Now, somewhere up here in the experimental setup, you will have a detector. The detector counts the number of projectiles hitting the projector in a given time interval. The detector has a finite size, and it covers a certain spatial angle as viewed from the target. So there's viewed from the target, there is a certain spatial angle d omega, which is covered by this detector. And in terms of ordinary angles, when we have the scattering angle theta, which is also we take as one of the angles in our spherical coordinates. The other angle that remains, that we still need, is the angle phi around the beam axis. Then this spatial angle d omega can be written as d phi d theta sine theta. That appears in the volume element in spherical coordinates. You have this d phi d theta sine theta. This is just an infinitesimal spatial angle. The incoming projectiles all have the same velocity. far away from the target. Far away from the target, they have velocity v, and let me write v at minus infinity. So still far away from the target. With that velocity, the projectiles have kinetic energy, E, that's mu half velocity squared, that's the energy. And they have angular momentum. Angular momentum is always defined with respect to a reference point. So here it is defined with respect to the origin, where the center of the potential is. Now the angular momentum is R vector product with P, and the magnitude of the angular momentum, the absolute value of the angular momentum, is then the distance from the beam axis, which is the impact parameter S, times the absolute value of momentum, which is mass times velocity. And we can, that's the angular momentum of the incoming projectile, still far away from the target. It has velocity v at minus infinity, moving parallel to the beam axis. So the associated momentum has magnitude mu times this velocity v at minus infinity, and to obtain the absolute value of the angular momentum, you multiply with the impact parameter. This is evaluated far away from the target, but since angular momentum is a conserved quantity, it has the same value throughout the trajectory. We can also express that with the help of the formula for the energy. We can express it in terms of the energy, that is the square root of 2 times mass times energy times impact parameter. Then let me introduce an important concept. It's a key quantity that is investigated experimentally in scattering experiments. That's the so-called cross-section, or more precisely, the differential cross-section. Let me first introduce another quantity that characterizes the beam, the incoming beam. That is the so-called current density of the incoming particles. Denote that by J, little j, that's defined as the number of incoming particles per unit time, per unit area. In letters, so the number of incoming particles, let me call that delta n0, in a certain time interval delta t, and a certain area delta a. So you can imagine you have here an area delta a, then you have projectiles passing through this area, this cross-section, this infinitesimal cross-section or small cross-section delta a, and you count the number of particles passing through this area per unit time and divide it by the size of the area. And that's called the incoming, or the current density of the incoming particles. Then you look at the particle current of the outgoing particles. Within this spatial angle d omega that is covered by the detector. So this is in fact the quantity that you will measure. That is the number of particles hitting the detector, delta n, in any given time interval, delta t. So it's the number of particles hitting the detector per unit time. This number of particles hitting the detector will, of course, depend on the spatial angle. The larger the detector, the larger the angle covered by the detector, the more particles you will have hitting the detector. And it will also depend on the scattering angle. So it depends on the position of the detector. So the delta n will be a function of the omega, and it will be a function of theta. But it will be independent of the other angle phi, the angle around the beam axis, because of symmetry. You have a central potential, and therefore in particular you have axial symmetry around the beam axis. Now with these two quantities, you can define the differential cross-section. And that is the following. It's the number, it's the particle current of the outgoing particles, so the number of particles hitting the detector per unit time, divided by the spatial angle covered by the detector, and divided by the incoming current density. Now, because you expect, of course, the number of particles that your detector will count will be proportional to the current density of the incoming beam. It should be proportional to the spatial angle covered by the detector, and should be proportional to the amount of time that you measure and that you accumulate data. So if you divide by all these quantities, then you expect a quantity that should depend only on properties of the potential, but not on properties of the beam. So let me first write this in a nicer form. And this is called the differential cross-section, d sigma over d omega, and that should no longer depend on the incoming current density, and it should no longer depend on the spatial angle covered by the detector, but it will still depend on the scattering angle. It will still depend on theta. And because of the axial symmetry, of course, it's also not dependent on the other angle phi around the beam axis. So this is the differential cross-section. It should depend only on the scattering angle, and of course it should depend on the shape and the strength of the central potential. And the basic idea of scattering experiments is that you measure experimentally the differential cross-section as a function of scattering angle theta, and then you want to deduce from that the form of the potential. When you integrate the differential cross-section over all the angles, then you obtain the total cross-section. So the total cross-section is defined as the integral of the differential cross-section over all the spatial angles, d omega. Now you can express the d omega again in terms of the ordinary angles theta and phi. Because of axial symmetry, you can immediately perform the integration over phi. That gives you a factor 2 pi. What remains is an integral over d theta, sine theta, and then you have the differential cross-section d sigma over d omega as a function of theta. Then you can calculate the total number of particles, of projectiles, that are scattered at all, i.e. Deflected by some angle theta different from 0 per unit time. So the number of particles, the total number of particles scattered per unit time. This is the integral over all angles. Then the number of particles scattered by an angle theta per unit time per elementary per unit spatial angle, and then you integrate over all the angles. But this is, by definition, this integrand is nothing but the incoming current density times the differential cross-section. You can take the incoming beam, a current density J in front of the integral, and what remains is by definition the total cross-section. So in other words, incoming current density times total cross-section equals the total number of particles that are scattered at all per unit time. This total cross-section has the unit of an area. Current density, that's number of particles per time per area, times the cross-section, which has the total cross-section, which has the unit of area, gives number of particles per unit time, and that's exactly what we were searching, namely the number of scattered particles per unit time. Therefore, you can visualize the total cross-section as a sort of effective area of the target. So you have incoming projectiles. You have your target. Then you say the target has an effective area which equals the total cross-section, sigma. And this means that those incoming projectiles that hit this effective area, they are scattered, and any projectiles that miss the effective area, they are not scattered, so there's no scattering. Now, if from this very simple qualitative picture, you can see that if the potential has a finite range, then you would expect that the total cross-section is also finite, because then any projectiles that hit or that pass the target outside this finite range, they are not scattered at all. Only projectiles that hit the target within this finite range are scattered at all. On the other hand, reversely, if the range of the potential is infinite, then the total cross-section may be infinite. Let me say a few more words about this issue of whether or not the total cross-section is finite or infinite. Let's look at different forms of the potential. If you have a potential that looks like that, as a function of distance from the target, you have a potential like that, with a finite range capital R. Then the total cross-section sigma will be finite. And in fact, in the following limit, where the potential inside this finite range becomes infinite, so you can think of this like a hard sphere. So you have around the center of the potential, you have a hard sphere, and a projectile hitting this hard sphere is deflected from the surface of this hard sphere. It can never penetrate inside the hard sphere. But outside the hard sphere, there's no It doesn't feel any potential at all. Yeah? So in that limit, actually, you will find that the total cross-section is equal to the area covered by this hard sphere, as viewed by the incoming projectile. So it's equal to pi times the range of the potential, or the radius of the hard sphere, squared. Let's consider as a second example. Let's consider a potential of, say, that form. For example, a Kepler type goes like 1 over r. This Kepler type has, well, loosely speaking, it's a potential with a long tail. It goes to zero at large distances. It goes to zero rather slowly. Yeah? So in that sense, it's it is a potential with infinite range, and it goes to zero rather slowly. In that case, total cross-section will be infinite. You can check that for the Kepler problem. We'll come back to the issue of how you calculate the cross-section, but you can verify that for the Kepler potential, the total cross-section is infinite. Then there is the sort of intermediate case where the potential also has an infinite range but goes to zero rather quickly. If we have, say, a Gauss shape, a Gaussian shape, so this also has infinite range, but it approaches zero quickly. Then it may happen that the differential cross-section, that the total cross-section is infinite, but it may also happen that it's finite. It really depends. It depends on the shape of the potential. The important parameter, variable here in such a scattering experiment is the scattering angle, theta. Let me draw once again the setup. We have the beam axis, we have the target, we have the projectile coming in, scattered off by the target. Asymptotically, it approaches this line here. We have the scattering angle theta. Now, the projectile comes in at a certain distance from the beam axis, which we called the impact parameter. Due to the axial symmetry of the problem, the scattering angle, theta, should depend only on the impact parameter. So theta should be a function of impact parameter. And qualitatively, we would expect that the further away the projectile is from the beam axis, the weaker the potential that the projectile feels when it passes the target, and therefore the smaller the scattering angle. So qualitatively, we would expect a monotonically decreasing function, theta as a function of s. And that we should be able to invert, and we should be able to find a function s of theta. Another aspect that I would like to mention for these scattering experiments is that the particle number must be conserved. The number of particles coming in, the total number of particles coming in, must equal the total number of particles going out. We don't consider experiments that absorb particles, but we have scattering processes where no particles are lost. So we should be able to formulate a balance equation that reflects conservation of particle number. Let us consider projectiles that pass through this infinitesimal ring. So this ring has radius s, which equals the impact parameter, and it has thickness ds. So s is finite, can be any finite radius, but the thickness of the ring ds is infinitesimal. So we cover an area, the ring has an area equal to 2 pi s times ds. The number of incoming projectiles passing through this ring per unit time is equal to the incoming current density times that area. So times 2 pi s ds. Now these projectiles, these incoming projectiles, are scattered off the target. Now consider first a particle with impact parameter s. So it's sort of at the inner boundary of the ring. Yeah, such a projectile is pretty close to the sort of relatively close to the target, and therefore should be scattered by this angle here. Then consider a particle that is at the outer edge of the ring. Now this is a bit further away from the target, and therefore the scattering should be a little bit weaker. So we would expect maybe behavior like that, with a resulting scattering angle that's a little bit smaller. So this here, the first particle that we had considered, that had a scattering angle theta of s, and the particle coming from the inner edge of the ring had the scattering angle theta of s. The particle coming from the outer edge of the ring had a slightly smaller scattering angle theta of s plus ds. So as a result, there's a small variation of scattering angle d theta, and this gives rise to a spatial angle d omega. So as a result of the small but non-zero thickness of the ring, we have, for the outgoing particles, a small but non-zero spatial angle d omega, in which we will find and measure the outgoing particles. So what is the number of outgoing particles in this range of angles between theta and theta plus d theta per unit time? It should be the differential cross-section, which is a function of theta only, times the incoming current density times the spatial angle, d omega. That's by definition of the differential cross-section. So by definition of the differential cross-section, this is the number of outgoing particles in this interval of angles. Now, first of all, we can write this in the usual form as d phi d theta sine theta. And since we consider the entire ring, so we consider all possible angles around the beam axis phi, we actually have to integrate over phi. Now, the integral over phi d phi, all the angles around the beam axis, simply gives us a 2 pi. Then we are left with j sine theta d theta and then the differential cross-section d sigma over d omega as a function of theta. Particle number conservation says that the number of incoming projectiles must equal the number of outgoing projectiles. So this expression here and that expression there, they must be equal. That's particle number conservation. You can solve that equality, this equation, for the differential cross-section, and you find that this is S, so the impact parameter, which we said is a function of theta, divided by sine theta times ds over d theta. And you take the absolute value of that because S is a monotonically decreasing function of theta, so the S over d theta is negative, but differential cross-section and all the other quantities appearing in this equation are positive quantities, so you have to take the absolute value. So this tells you if you know the scattering angle as a function of impact parameter, then you can invert. Then you know the impact parameter as a function of scattering angle. You can insert this into this equation and you can calculate the differential cross-section. So what you have to do is that you calculate theta of S. This is something that you can do if you know the form of the potential, and what we are going to do next time for the Kepler potential, scattering angle as a function of impact parameter. Then you invert to get S of theta, and then you insert this into the formula above, and you get the differential cross-section d sigma over d omega. What you do in a scattering experiment where you want to learn something about an unknown potential is that you try to go the other way around. You measure the differential cross-section. From that you try to infer S as a function of theta, and by inverting you want to infer theta as a function of S, and that in turn gives you important information about the shape of the potential.